Good afternoon, and thank you for joining RadSite's webinar, Moving to a Uniform Physics Testing Protocol for Cone Beam CT Imaging. Before we begin, I would like to go over a few housekeeping items. Today's presentation will be recorded, and an email containing the link will be sent to all registered participants early next week. To minimize noise and distraction, all attendee phones have been muted. However, if you have a question or comment during the presentation, we encourage you to submit it using the chat box section on the lower right side of the webinar portal. We will do our best to address all questions and comments at the end of the presentation. I will now turn the presentation over to our moderator, Dr. Elliot Siegel, RadSite's MAP Standards Committee Chair. Dr. Siegel.
Thanks, Joy. It's a pleasure to have the opportunity to moderate today. I'm really very much looking forward to the discussion and the presentations. Many of you will recall that we've done a recent webinar on cone beam CT, talked about some of the clinical applications of cone beam CT, talked about some of the billing aspects of cone beam CT, and we promised you that we would come back and talk a little bit more in detail about some of the considerations with regard to testing of cone beam CT, some of the physics issues associated with cone beam CT that you need to know in order to buy cone beam CT and evaluate the quality of cone beam CT also. As many of you know, cone beam CT is a fairly misunderstood modality in comparison to CT, and I think many of we radiologists really don't understand exactly what the differences are and the implications. And one thing that I think most people don't know are the really profound differences in some of the metrics that one might use to describe things as simple as comparing radiation dose with cone beam versus non-cone beam, or being able to evaluate image quality, or even to be able to talk about, relatively straightforward concepts such as slice thickness that we take for granted in CT when we try to apply it to cone beam CT. So we have three really extraordinarily experienced experts who not only know the space, but also have helped to define the space. And so it's my privilege to introduce our three panelists, who include John Boone, a PhD, who's professor of radiology at the University of California, Davis, and holds an appointment in the Department of Biomedical Engineering there. Also, Jeff Sewardson, who's the John C. Malone Professor and Vice Chair of Biomedical Engineering at Johns Hopkins University, with appointments in radiology, neurosurgery, computer science, and the Armstrong Institute for Patient Safety and Quality. And then Joshua Levy, who has more than 30 years of phantom design experience with a major focus on CT performance analysis. And so, we're really talking with three of the most experienced people in the entire country, I believe, with regard to the cone beam technology. And we'll have some presentations, make it interactive, and try and make it as practical as possible. And I'll have some questions, I'm sure, but if those listening have questions, be really delighted to take those as well. So, Julie, let me turn slides back to you, and we can go ahead and get started.
Thank you very much, and appreciate that introduction, Dr. Siegel. So today we're talking about the emerging standards for physics testing in cone beam CT. And let me just point out that Jeff Sewardson actually did his PhD on the development of flat panel detectors, which in many cases was the enabling technology that allowed cone beam CT to actually become a real modality some years ago. And you could see the rotating head below. Jeff was instrumental in the development of IGRT, image-guided radiation therapy, where most patients who undergo radiation therapy have a cone beam CT scan prior to their daily treatment to make sure that they're aligned properly with the treatment beam. The second slide at the bottom shows his current work on essentially image-guided surgery for head and neck and spine surgery, as you can see illustrated there. I'll draw your attention to the ankle picture over to the right. Jeff has also been involved with a commercial company to develop what is now available commercially MSK, bone imaging system for extremities, and you can see the detail visible there. My own involvement with cone beam CT has been over the last 20 years, where I've worked on the development of breast CT systems, and have developed 4 systems, and that's now in commercial fabrication discussions with various companies. Josh Levy's been involved in making phantoms for imaging, not only in X-ray, but other modalities in radiology, and you can see this beautiful phantom that we'll be talking about today. He's got 40 years of experience in this. So as Elliot said, we have some experience in this space of cone beam CT imaging. Next slide. There you go. And our universities, for Jeff and I, require that we disclose any conflicts here and acknowledgements as well. Too long of a list to go into, but let me just point out the pink slides down there. We have had an active relationship with folks at the precursors of RadSite, especially Gary and Elliot, in developing some of the written requirements for consistency testing and acceptance testing for cone beam systems, since we have both been involved in designing and building and testing cone beam systems, as I've just described. And we've also simultaneously been involved in developing, the object that is the tests are centered around, and that's the phantom, the Corgi phantom. And Josh Levy has been instrumental in working with us, really as a collaboration more than just a licensee, in the development of that phantom. Next slide, please. So this is an outline of what we'll be presenting this morning in my time, and probably this afternoon and for most of you. So the evolution of systems and testing standards. Well, I'm a board certified medical physicist with 35 years of experience in radiology, and doing clinical testing as one component of my job. So I hope to show you some of the lessons that we've learned from diagnostic CT, which I'll refer to as whole body CT, to differentiate it from cone beam CT. And of course, over the last few years, we've seen the proliferation of cone beam CT systems for various dedicated applications. And I think the purpose really here is to develop and talk about the need for emerging standards for cone beam CT systems for both dose, radiation dose, and image quality. Jeff will talk about cone beam systems, as you see a medley of images of those on the upper right, and for both diagnostic with dental, ENT, ortho, musculoskeletal, and breast, and interventional, which is really his area of expertise, with interventional radiology, image-guided surgery, and image-guided radiation therapy. And then Josh will kick in with a discussion of the phantom for CBCT physics testing, and also the software that we've developed to analyze the image data that's produced by the phantom to produce a semi-automated or fully automated quality assurance report. Next slide, please. So lessons from the 50 years of whole body CT, and I will just say that, of course, we benefit from those lessons, but we go back to the early days of the AAPM, the American Association for Physicists in Medicine, that Jeff and I, and to some extent Josh, are involved with. They have really taken the lead in developing many of they're really just called task group reports, but many regulatory agencies, including the Center for Devices and Radiological Health, which is part of the FDA, members of CDRH employees sit on many of these task groups and weigh in on the performance standards and testing methods that are written in these pages. Also, the FDA has sort of agreed to defer to the international body called the International Electrotechnical Commission, and they develop standards for a wide cross-section of devices in medicine, including CT scanners. And so I participated in that, and so has Dr. Sivertson. The benefit of this is that we can learn from this long breadth of experience. One of the issues that I think is exciting with what we're talking about today is we're starting at the beginning of cone beam CT sort of quality assurance and dosimetry. The problem that we've experienced with these task group reports is that they've been incorporated into standards, as I alluded to, but many of them have actually been incorporated into state law, and that's very difficult to change. So we have 50 states in the US, of course, and to go around and lobby the legislators in those 50 states to change as technology has advanced has been very difficult. So a little bit of the story of 50 years of whole body CT is the standards came out a long time ago. The technology has advanced, but the standards, the regulations really haven't advanced to address the new technology. We sit at the threshold of this new technology of CBCT, which is sort of exciting for me at least. Next, please. So just to dig in, as a board certified medical physicist with some responsibilities here. So the state laws that I referred to use this phantom shown in the upper left, and this is the methodology shown pictorially, and I won't go into that, but you can see the phantom in a CT scanner below. This is a 32 centimeter diameter, 15 centimeter long phantom for body, and you can see inserted within it is a head phantom, which is 16 centimeters in diameter. This thing, you know, a lot of people can't even pick it up. It's pretty heavy. It comes in a cart with wheels, and that's just one of the tools, and its only function is to measure dose. It doesn't measure image quality, and we'll talk about that in the next slide, but I've been very active with new dosimetry metrics, as you see in the right panel, and that phantom design picture is from my lab. And I, some years ago, was trying to push a standard related to a more accurate phantom. Key to the measurements here, though, are current standards require a 10 centimeter long pencil chamber, which is a little bit cumbersome in today's standards. And we've sort of gone to a smaller chamber, which has a 18 millimeter active length, as you can see in the farmer chamber picture in the upper right with my hand there. And so that has a lot of, I won't get into the details of how that benefits dosimetry, but take my word for it that it does. And makes it a much easier test once you're at the scanner. Next slide, please. And so we're talking about dose and image quality, and so for computed tomography, the American College of Radiology, the ACR, developed with physicists, of course, the well-known ACR CT phantom, as you see pictured here. And it uses sort of the old paradigm of measuring image quality, where you measure the individual sections that I'll go through in a sec. And the top one that Jeff's pointing to here is the so-called low contrast section. And the role there of the physicist is really to eyeball that and see if you can see, you know, how many of the circles that are very subtle and are hidden in the noise. So this is an assessment of the noise, or the contrast to noise ratio, or the contrast resolution. A more modern way to do that would be to apply some mathematics to the images and compute the noise power spectrum. And now you have a quantitative tool that's not subjective, that's not dependent upon the lighting conditions that the physicist was in when he or she were evaluating the images, and so on. And so this gives us a solid measure of the noise properties of the scanner, the noise power spectrum. For spatial resolution, which refers to the ability to see small detail, the traditional module in the Phantom is just a bar pattern that's really been used since the beginning of radiology. And what we propose is to measure what has become a default standard in many, certainly the vendors use this, the modulation transfer function. And the XY refers to the axial plane on a whole body CT system. And you can see the dependency of the various kernels that are used in whole body CT on these plots. Again, a quantitative measure of spatial resolution that would be very useful to measure annually. And so you can see if something's changed, if the focal spot has degraded and your resolution has degraded. You're never going to pick that up on a bar Phantom.
So John, just to make it clear, we're not talking about old style Phantom versus new style Phantom, talking about CT versus cone beam CT. What you're talking about essentially is a fundamental change in the way that we think about CT Phantoms in general, whether it's what we think of as conventional CT or what you're calling whole body CT, or alternatively cone beam. You're suggesting a new paradigm for measuring CT metrics and performance that would encompass all types of CT, right?
Exactly, and thank you for that excellent comment. I'll just point out that I've been given those slides I developed 13 years ago when I was giving categorical courses at the RSNA. So I've been trying to preach to the community how we should go from these qualitative metrics to the quantitative metrics in whole body. And what I tried to refer to in the earlier slide is the problem is that some state laws require that you use the old metrics. In fact, most state laws require that you use the old metrics. And so it's been a little bit fighting tooth and nail to get newer, more modern quantitative standards in with whole body. But we're at the precipice of standards for CBCT, so we can enjoy these new quantitative metrics now as we develop the standards for that. So that's what I find to be very exciting. And, you know, I think I've conveyed what's on this slide. So maybe we could move to the next one.
John, is the requirement by the states for reporting using the standard metrics of what you're calling the old paradigm, or does it require you to actually test using the old methodology? Is it possible to map out the acquisition of what you're doing with the new paradigm to be able to then report it using metrics that would conform to what the state's doing, or is it that they're specifying how you actually acquire the data?
Well, that's a good question, and the answer sort of differs if you're talking about dose or image quality. For dose, the state sort of requires for CT that you measure, at least the state I'm in, and this is true for many others, that you measure the CT-DI vol as what it's called, the computed tomography dose index, and that has a so that impacts the way that you measure it using that 32 centimeter diameter Phantom. For image quality, it's unclear. The state regulations in California say you need to measure image quality, and I haven't read them recently enough to say if they're mandating the MTF, but that's what we would like to have them do. I will say, Elliot, that a lot of the states are now deferring to accreditation, and the American College of Radiology Phantom that I showed is part of their accreditation program. And so the state will just look to see if that scanner is accredited, and then by default, they're accepting the dosimetry metrics and the image quality metrics and some other metrics having to do with the people who are reading and the people who are taking them. And the technologists, the radiologists, and the physicists. So that has become a more recent thing in the last 10 years where the states are deferring to an accreditation procedure. But
thanks, John. That's super helpful.
Yeah, thank you. But those, the ACR accreditation is not a quantitative thing. It uses the old eyeball analysis, as I'm trying to show here. So, just going through this a little bit, what we're talking about in the old era, the Phantom was complicated, it was expensive, had a lot of these modules that you can see in that picture. Those take money to build. The new era on the right there is a basic Phantom, for instance, to measure noise or even resolution. The analysis itself in the old paradigm was simple. It was just an eyeball on an image, very qualitative, of course. And what we're proposing for both the whole body and cone beam is a more sophisticated, mathematically based quantitative metrics that really can tell you fine differences in the performance between scanners or with one scanner over time. And hence the results that we're really getting in the old era are perfunctory. You're just doing it to pass the laws. Rarely do these things fail. Whereas with the new era, new Phantoms, new math, we can have a useful and quantitative outcome that we can actually use to guide protocols and other issues in our programs. And with that, I think I'm ready to pass it off to Jeff. Oh, one last slide for me. So what I've sort of talked about is, fan beam CT, which are mostly whole body CT systems, and they have increased the multi-detector array CT systems, MDCTs as they're called. And you can see on this slide in time how the beam width has gotten greater in whole body CT. And what we're really talking about today in cone beam CT is much, much greater beam width. There's a couple of commercial whole body CT scanners that have a 16 centimeter aperture at this isocenter, but what we're not really talking about those today. We're talking about cone beam CT systems, and that's the width of the cone that we're sort of talking about in today's system.
Great, thank you, John. This is Jeff Sewardson. So picking up there with cone beam CT, as you may know, this technology emerged approximately 20 years ago in two very different areas. On the one hand, in dental imaging, and on the other hand, in image-guided radiation therapy. This shows a couple of examples of those. Interesting to see those emerge in such different areas. They both have the same underlying principles of a broad volumetric beam and the ability to reconstruct a volume from a single rotation about the patient. So it's without a helical motion of the patient, just it's one turn of the scanner gives you the volume. And the landscape that has emerged based on that technology over the last 20 years is pretty broad. And this drawing just shows a few of those over a spectrum ranging from image-guided procedures in radiotherapy, surgery, or interventional radiology, through to diagnostic imaging in dental, ENT, breast, and orthopedics and musculoskeletal. And so as John described and Elliot remarked as well, the need to evaluate and have more reliable and quantitative physics testing standards for this technology is imminent because many of the old standards break. And that in applying those newer, more quantitative metrics, we find that they're actually applicable to whole body MDCT as well. You'll see that. The difference between these two technologies, I'll try to go relatively quickly. In this column, you see typical characteristics of a multi-detector CT scanner. In this column, characteristics that are typical of this very broad range of cone beam CT systems. They differ in many ways. The X-ray source of a CT scanner tends to be pretty high power, delivering continuous current, compared to lower power, conventional pulsed radiographic or pulsed fluoroscopic X-ray tubes. The detectors in a CT scanner tends to be one of very high quality detectors of multiple rows, but covering a relatively small range in Z. Although that has changed, certainly, and I mean, for many years now, you've got 320 row scanners that cover a whole organ. But in cone beam CT, that's the norm. You have a greater number of rows, a large volumetric coverage, and you get that entire volume in one sweep of the scanner. Rotation speed tends to be very fast in helical CT and relatively slow, order of magnitude. So whereas helical CT is going at 3 rotations, or let's say 5 rotations per second, a cone beam system might rotate once in 5 seconds. And in fact, that would be fast, typically more like 30 seconds or 60 seconds for a rotation. The orbit, obviously helical in helical CT compared to circular, or actually some very flexible non-circular orbits on things like C-arms. The image quality here tends to be excellent diagnostic quality of bone and soft tissues. Of course, there's a lot of advanced protocols for contrast enhancement or dual energy and so forth, whereas the image quality in cone beam tends to be moderate. It does have isotropic sub-millimeter spatial resolution, and so there's a spatial resolution advantage in this technology that comes somewhat for free, but it's challenged in its contrast resolution or its visualization of soft tissue structures by scatter, noise, and a number of artifacts.
And Jeff, is that an inherent limitation of the technology, or is it a manifestation of the fact that cone beam has evolved to optimize visualization of teeth and bones and sinuses, et cetera? Or is this something where cone beam CT will always have those challenges as far as noise, artifacts, and scatter? And is it also inherently related to the slower rotation time?
It is. So it's not, so I would say they're relatively fundamental and getting better all the time, but they are fundamental within the technology. Larger scatter fractions by virtue of the volumetric cone beam. Higher noise because of the large area detectors tend to have higher noise characteristics than row detectors. The artifacts, like you said, slower scans mean larger motion artifacts. So most of these are fairly fundamental to the technology, getting better and better all the time, but they do face intrinsic challenges relative to what you have in multi-detector fan beam CT.
Okay, thanks.
Thank you. And the application space is similar, but a little bit inverted, whereas the diagnostic space is the main domain for helical CT with some interventional CT systems, and then a lot of applications of cone beam and image-guided procedures, radiotherapy surgery, and interventional radiology, with some diagnostic applications emerging, breast, for example. Well, I'll have to go faster. The emerging standards for cone beam CT address factors that are shown here, and some of the things that distinguish cone beam physics testing from helical are listed here. We need dosimetry that's appropriate to a volumetric beam. John commented on that, and that requires some rethinking of what the form of the ion chamber is. It needs to allow properly measure the increased scatter contributions to the dose, and has to accommodate half scan protocols and other orbits of the source and detector. It's not just a circular helical scan all the time. Levels of uniformity and accuracy tend to be lower in cone beam CT due to some of the factors that we just mentioned, Elliot, and that the accuracy of Hounsfield units may not even be possible in some systems, and probably isn't nearly as standardized for cone beam systems. Contrast tends to be suitable in most systems for bone visualization only, but there are systems emerging, of course, that need to substantiate claims on soft tissue visibility. The noise, as we said, tends to be higher in cone beam, and we need to be able to have a more quantitative view of the role of low dose protocols and the electronics noise. And as we'll see, that describes new metrics that are what John said is the noise power spectrum that defines both the magnitude and the texture of the noise in order to give that level of quantitation. The spatial resolution in cone beam CT is beyond what you could reliably assess through conventional qualitative subjective measures like line pair patterns, but it's also 3D. It's an intrinsically fully 3D modality. So we need to be able to characterize the spatial resolution in all 3 dimensions beyond something like as just slice thickness, and to substantiate claims of isotropic resolution. And finally, cone beam CT suffers all of the same artifacts as multi-detector CT, but usually to a greater extent, and introduces new challenges with respect to something called the cone beam artifact, which one should understand with respect to any system that they're using. So a phantom that John and Josh and I have iterated on and developed over the last year or more is shown here. And it's called the Corgi phantom, just because it has a Corgi-like cylindrical shape, a form factor. It doesn't stand for anything. The phantom is multi-purpose in that this phantom, unlike a CTDI phantom or ACR phantom, is really designed to provide measurement of both image quality and dose. It's in a form factor that's suitable to that broad variety of cone beam systems that I showed, everything from dental to IGRT. This system is designed to be able to configure in ways that are suitable to any one of those scanners. It's modular, so that if something has a particular beam geometry, the modular design of this phantom allows the phantom to be restacked. It's quantitative. It's consistent with the physics metrics that John Boone described earlier. The analysis of images coming from the phantom is automated and generates a structured report. So it doesn't rely on a medical physicist in Excel or MATLAB or something like this. It's very streamlined software that we'll show in a moment. And interestingly, it's generalizable. So this closes the loop, as Elliot was describing earlier. This phantom can be adapted to the same kind of physics testing in whole body CT and provide the benefits according to that. This shows a shorter stack that might be suitable to a dental scanner.
Jeff, when you talk about generalizability, if I did a sinus CT scan with a whole body CT scanner and it told me that I was delivering, say, 6 millisieverts, for example. Mm-hmm. Can I make a measurement on the Corgi phantom that would allow me to determine that a patient who was scanned on a cone beam CT scanner who had the exact same amount of dose actually did have that same 6 millisieverts, or would that be apples and oranges? Can one generalize the actual dose to a patient in a manner that would allow one to directly compare whole body CT in comparison to cone beam?
Yeah, so there's two, so as you know, Elliot, you're on the edge of a complicated space of effective dose. And so there are some factors of radiation biology, which we don't need to talk about today, that would differentiate one's description of the effective dose of a sinus scan versus, let's say, an ankle scan. Okay. But if I can back one step back from effective dose and millisieverts to absorbed dose in milligray, which is what we measure in both the CTDI vol with in what I'm going to show you here with the Corgi, that's milligray. And yes, that is an apples to apples description of how much energy was absorbed per unit mass, okay, by the patient. And now whether that was in the head or the ankle, that's where the radiation biology question comes in and an effective dose calculation, okay? Sure. But as far as the physics testing, it's apples to apples.
Thanks, that's helpful because I know when I have shot for cone beam CT, I have not been able to get an apples to apples comparison. So it's really great that that will be one of the capabilities of the system. Thanks.
Thanks. That configurability and generalizability is illustrated here. Here's me walking it around various systems in the hospital, including a helical CT scanner. And this is a snapshot of the kind of structured report you get actually from just a drag and drop of the DICOM data onto the software. And as you see, if you have DICOM, it extracts DICOM information from the scan data. And then it computes a number of these metrics that we're going to talk about: uniformity, noise, spatial resolution, cone beam artifact, and so forth. And we'll come back to this. I'll just give you a preview of it here. But so here's a CAD drawing of the Corgi that Josh has put together very nicely. It shows a stack of 5 modules. There are two basic modules within that. One which we sometimes refer to as the test module, and one which is really just a uniform medium of polyurethane plastic. In the test, each of these serves a different function within the phantom. The uniform phantom includes these pass-through holes, right, for feeding the ion chamber. It's also the support structure for the phantom. There are threaded rods that hold the phantom together within these holes. There are these test objects shown here. Each one of these is a different contrast. We use that, of course, to do Hounsfield unit accuracy or sensitometry, but also contrast to noise ratio. And as I'll show you, spatial resolution. We actually pick all those measurements up off of these test objects here. And then there's one interesting other insert, which we'll come to at the end, which is this little stack of discs here, which is a measurement of the cone beam artifact. So if I may, I want to step quickly through the application of the Corgi and all of these things, starting with dose, where, as I said, we use these central and peripheral chamber holes for the passage of a Farmer chamber, which is that smaller chamber that Dr. Boone showed earlier. The dosimetry for volumetric beams is fairly well known in radiotherapy, but has really only come to light in cone beam over the last 15 years. And so groups like my own and at Stanford started talking about cone beam dosimetry in the early 2000s, and that has more recently started to become quantified by the AAPM or codified by the AAPM, because really many of these principles apply to multi-detector CT, right, which also now employ volumetric beams. It's not just that narrow fan beam. And so this methodology is becoming more appropriate to MDCT as well. This just shows the Corgi with a Farmer chamber passed in. The method that emerges from that is basically a measurement of the dose, the absorbed dose in milligray at the center and periphery with a Farmer chamber. And there's a weighted combination of the central and peripheral dose, which gives you this weighted dose in milligray. All right. And that can be done with as few as 2 measurements, but as many as 3 or 4. Here's an example of a long stack with a Farmer chamber on a head scanner. And what I want you to see here is not only do we get 4 dose measurements, but you see that for cone beam systems, it's not uniform, right? And so many of these systems use what are called half-scan orbits, that the dose distribution is quite non-uniform. It's important to understand that that the dose across the back of the head might be 4 times higher than across the front of the head. And certainly that might affect your calculation of effective dose, Elliot, right? If anterior organs have higher radiosensitivity than posterior organs and so forth. But this is the norm in cone beam CT. Many systems actually deliver this. Multi-detector CT tends to be circularly symmetric, but this is part of the reason that cone beam dosimetry requires something new. Here's 2 examples of that. Here's a angio cone beam CT system. Here's a radiotherapy system. This one, if you're seeing my mouse, I hope, does a half scan. This one does a 360-degree spin. And so you see how that dose distribution is quite different between the 2, even though the dose itself, the weighted dose combination is about the same. The dose absorbed by the patient is quite different in those 2 scans. So if I may, I want to roll through other things that the Corgi measures automatically from just 1 scan of the Corgi. The first being uniformity and the accuracy of Hounsfield units. So here I'm just showing uniformity. So that's basically a measure of cupping within the image. And so here are 2 systems, a scan of the Corgi. This system hasn't put very much effort into its scatter corrections and shading artifact corrections. And so you have a relatively strong cupping artifact, and maybe perfectly suitable to what this system is designed for. But as opposed to this one, which is a diagnostic scanner for orthopedics imaging. And here you see a high level of uniformity and a low cupping artifact effect. So this is a line profile through that image, right? Deeper cupping and then a relatively flat image. The hole in the middle, of course, is this hole for the ion chamber. Contrast, we go down to the test module. This actually shows an earlier version of the test module, but you see these different plastic materials. They're each indicated here by an abbreviation of some different kind of plastic. And as you see, they present a different contrast. The contrast to noise is just the difference in the signal between the foreground and the background and the average noise. And this just shows you the contrast to noise for two scanners running in very different protocols. This one's running a very low resolution protocol where the contrast to noise ratio is very high, right? Negative contrast just means it's dark. And then this scanner running in a very high resolution protocol where the contrast to noise is less, simply because the system is running at a higher resolution mode. I want to talk a little bit more about noise, because this is something where an eyeball test simply won't do. But conventionally, even just measuring the standard deviation is missing a lot. And I hope I can illustrate that here by showing you that the same noise magnitude can get very different levels of conspicuity and visual quality. So these three images show noise distributions, just quantum noise, with the same standard deviation. So that's what you would measure. And so a conventional metric would characterize these systems as exactly the same. What's different about these is their texture or spatial frequency content. And that can be affected by many things in the scanner. And if you look closely, you'll see that I've superimposed a little stimulus that I want you to be able to detect. This might be a microcalcification. And you see that the detection of that same stimulus, the contrast of that little speck is the same in each of these, but its conspicuity is quite different to your eye. I'm sure you could agree that and basically it means that when the noise texture is very similar to this texture of what you're looking for, well, that challenges the visual task. And so here it is shown with a different kind of lesion. Here's a larger lesion, a low contrast lesion. And so whereas on the previous image, which you see here, you might have concluded, well, this is the system where this is the mode where I can see high resolution details better. Your answer would change and say, this is the system where I can detect lower. So that's interesting, and hopefully tells you that understanding the noise in terms of its texture is important. As John Boone mentioned, that's characterized by the noise power spectrum. There's a little bit of math by way of the Fourier transform of the image, and that gives you the type of spectrum that John was showing. That's extracted automatically from the uniform region of the Corgi. So a couple of those systems we saw before, and here's the noise power spectrum. So we're in the Fourier domain. These are similar to the curves that John was showing earlier. It's just showing you a two-dimensional view of it. And these two systems cover very different regions of the frequency domain. They sample, this one is much higher resolution, and so it spans out to a larger range. But this gives you a quantifiable view of the noise texture. And if that noise texture is changing in time, or if it's something that you want to consider in setting protocols for visualization of fine detail versus low contrast, this is a far more suitable method. And also, this is actually a really good trap of certain failures that a system can start to undergo. So for example, if one of these pulsed fluoroscopic tubes is starting to arc or missing frames or something like that, sometimes those can be a little bit difficult to see visually, very conspicuous in an analysis of the noise power spectrum, where you would see a streak pop right out as something anomalous, something in the system has changed, the repeatability of the tube is failing or something like that. So it's actually a pretty good constancy check as well. Moving to spatial resolution, John mentioned the conventional eyeball test. It's subjective, it's qualitative, it's not reproducible even within one observer, and it's prone to error. Here's an example of a line pair pattern in the CAT fan, which is from the Phantom Laboratory. And here we just show three scan protocols at different spatial resolution. And I don't know that any of us could agree as to exactly which is the least visible line pair. But I want to mention that it's actually prone to error in interesting ways. For example, cone beam CT systems need very accurate geometric calibration. And sometimes when the geometric calibration starts to fail, your C-arm is banged around in the hallway and so forth, and that can actually come through in interesting ways. And one way is that it can give you kind of false, in this case, it would appear as false information in a line pair test, where in fact, you see how this actually looks like a pretty good representation of a line pair pattern. If you start to look closely, these things on the edges don't quite look right. And in fact, it's an artifact of geometric calibration error, where what you're seeing here is a false aliasing effect. And we're actually above the spatial resolution limit, and the modulation we're seeing in this little line pair test pattern is purely artifact. So, by the way, also these things, this approach only gives you a view of the spatial resolution in the axial plane, so it's not particularly well suited to characterizing the 3D spatial resolution. Also, it's not suitable to iterative reconstruction methods or nonlinear reconstruction methods, which are increasingly common, simply because these tend to be pretty high contrast, fairly easily tricked by a nonlinear iterative reconstruction method. So John mentioned the MTF. Again, we see the Fourier transform and a way of extracting the spatial resolution properties from either the point spread function. We'll actually show you a way where we get it from the edge, or the edge spread function of those test objects. So here they are. Those are those test objects. We look at the edge of those test objects in the axial plane. That allows us to measure the MTF in any of these directions in the axial plane. But notice that those inserts are rounded off. There's a hemisphere there. And what we can do is we come up along the edge of the hemisphere, and we can analyze the spatial resolution in any direction, right up into the Z direction, right? Or this 45-degree direction. So you really have a probe now of the fully 3D spatial resolution characteristic in any or all directions. And this shows you a couple of systems where, actually here I think I'm showing the MTF at 45 degrees. So it's a nice simple characterization of the overall resolution of these systems. Here for an angio system, here for a higher resolution system. This is the breast scanner, and you know it's higher resolution because its MTF is higher out to a higher spatial frequency, about double the resolution of this system. All right. I'll round that out just by saying a few things about artifacts. On the right hand of this slide, you see all the artifacts, that are typical in helical CT, but exaggerated in cone beam CT. And one that's relatively new. This is associated specifically with a volumetric beam or a cone beam, which is acquired on a circular orbit with that cone beam. The cause of this artifact is incomplete sampling in Z. So what is it? This is a coronal image of a stack of CDs with a little sphere just sort of separating out each CD. So this should appear to be as just a nice stack of horizontal lines. But you see how those horizontal lines are blurred out, and they're blurred out worse as you go farther from the center of the volume. So that effect is evident in many ways: shading, streaks, and distortion off of flat edges. So I'm just going to talk about that one. Again, going to the Corgi, where there's this interesting object in there. It's a pair of discs, and here if I look at a coronal image of that pair of discs, now I've got a standardized little test object where I've got two discs, and what we measure here quantitatively is the modulation in the signal, the variation in signal between these discs. So we look at the difference between the signal in the disc versus the center, and that's a number now that we can hang on to say how severe is the cone beam artifact. And here is an example of that on, again, a couple of systems. So if you remember, the Corgi had two of these test modules, one near the center of the beam and one up at the fifth module in the stack at the edge. And so what you see is at the center of the beam, the discs are pretty well resolved, and they are less so up near the top of the field of view. And so the Z mod associated with the center of the field is higher than the Z mod at the edge. And so here is something that we could quantify and understand the role of the cone beam artifact within a system. And this gets pretty complicated. Some scanners tackle this effect head on. For example, this scanner actually incorporates 3 X-ray tubes arranged along the Z direction specifically to reduce cone beam artifact. And it actually accomplishes that. So here you see that the Z mod at the center of the beam is about the same as the Z mod at the edge of the field. And that's by virtue of the design that's built into that scanner. All right. So I mentioned that the way of analyzing all the things I showed there is actually automated, and here's that structured report again, which fetched DICOM data if it's available out of the scan. And all of these measures are extracted from a single scan of the phantom. And with that, I actually want to ask Josh Levy to describe how that automated image analysis is being implemented at the Phantom Lab, including a cloud-based service.
Thanks, Jeff. Josh Levy here. Basically, what we have is this SMARI cloud-based platform. And one would scan their Phantom, grab the DICOM images, upload them to the SMARI portal. Once they're uploaded, the automated analysis actually looks through all the slices, figures out which slices need to be used for different measurements, and produce a complete report. Now, that's the underlying thing, but we also have this sort of wonderful database structure on the cloud, the SMARI system. And basically how that service works is you start with the ability to organize your data. For example, in this sample slide, we have 2 different locations, the Saratoga Dental Clinic and the Yorktown Imaging. And then for each machine, you can set up your own sort of data collection. And in some cases, you may have like a high resolution in a standard mode or multiple modes that you want to operate, different arcs or whatever features, and you can collect those data separately so that you can actually compare apples to apples. And also in other cases, you may have a daily check versus a monthly check. And so the data is there, it's collected in these sort of database bins. And on the next slide, I can talk to you a little bit about some of what we can do with that data, along with providing a report. And you can actually format to some extent how that report is organized. We have this data so you can go back and look over time. So what we're looking at is 2 different plots here over time, showing how the Delrin CT number has changed. And on the right, we're showing how uniformity has changed. Now, if you want to start moving into statistical process control, this stuff is beautiful because it helps you to really understand what your variability is and precision of your systems. But also just as a diagnostic thing, if you have a report that's a little high or a little low and you want to go back and look at history, is this just a weird blip, or is there a trend? Is your machine starting to drift, and is it a good time to call service before it gets too bad? And finally, on the next slide, I can talk a little bit about, with that data, we can also compare either different machines or different modalities. So what we can do is we can take, for example, here we're looking at noise tests, and we're looking at 2 different machines, and it's showing you where that whole array of data we have comes out. It's a very powerful platform, along with what I've already described. You can actually set pass-fail limits so that, let's say you have a technologist who runs a Phantom on a daily check and uploads the data. If something that's reviewed is not within spec, emails can go out saying something is out of limits. You can also customize your reports. If you want to have your noise number first, you can move that to the top of the report and do that kind of thing. In a case where you want to have a physicist who's overviewing the technicians who are doing the daily checks or whatever, you can actually have report sign-offs where the physicist would review and sign off, and there would be a record of that. There's automatic email notifications of things like that a new report has come up, and the system can manage multiple users where different users have different sort of power to do different things. A technician may only be able to see the machines they work on, while the overseeing physicist can see everything. And
Josh, could you imagine a scenario where one might be able to have reference data and compare to other sites? So for machines like mine or sites like mine, maybe within my network or maybe across networks, and could you see maybe a baseline of some standard data to see whether I'm an outlier in the metrics that I'm getting from the analysis?
If customers are willing to share blinded data, and what I say by blinded is it's institutionally blinded, we can let them see other blinded data too, so that let's say you have a Model X scanner and you're using a number 3 protocol. If you wanted to look and see how your system compares with all the other Model X's with the number 3 protocol, that data would be there. Now, this is brand new with the Corgi, so we don't have that kind of data available, but ultimately that kind of thing would be there. And along with, if you have several machines yourself, with this comparative function, you can compare, your 3 different, brand X dental CTs and see if they're all performing the same on their noise or MTF or whatever features you're interested in.
Thanks, Josh.
So that's our presentation, I believe. So we're open to any questions.
Yes.
Last
Go ahead.
couple
I'm sorry.
here. So just to mention that the Corgi Phantom has applicability to helical CT. Jeff, do you want to play that movie? And so is it applicable to CT? Yes, it is. Does a Corgi address testing shortfalls in MDCT? Absolutely. The MTF is a classic. The ACR Phantom, when we bought it, was $7,000. Do we need to buy a new one to address the fact that our CT scanners do much better resolution than the bar patterns allow on that system? Does the Corgi smart software that Josh just showed work with the MDCT data sets? You betcha. They're DICOM data sets, and they plug right into this software as well. Next. So in summary, Jeff did a great overview of the expanding landscape of cone beam CT with all the different applications in both diagnostic and interventional. And what we've really experienced, and I think that RadSite wants to get to this issue, is a 20-year dearth of physics testing across these systems. And we desperately need some standards and accreditation processes to help us move into the modern era. We do believe that the Corgi Phantom was designed to measure the parameters that these are crucial to understanding the performance of these many different types of cone beam CT scanners that Jeff so nicely outlined. And it just happens that the design of the Phantom lends itself to the extension to helical multiple detector CT systems as well, with both the 16 and 32 centimeter annuli. And per a previous question, it addresses the dose issues as well. And with that, I think we are concluded.
Great, thanks. That was really excellent, really fascinating. I don't see any questions, and the time is the hour's drawing to a close. But I had one question to close off, and that is the AAPM has written a tremendous amount about what we've referred to as whole body CT, as far as requirements and as far as standards. Where is AAPM now with regards to doing something analogous for cone beam CT? And so will AAPM sort of recognize maybe this new paradigm that we're talking about as far as the phantoms? Will AAPM have more specific recommendations for metrics and standard ways to measure them for cone beam CT? Does that exist already? Is that in the 1-year time frame, 10-year time frame?
I think I can address that. It's certainly not within. There's no real active group. I happen to be the chairman of the CT subcommittee where you would think that this would lie, and there's no active group that is studying performance metrics in CT, in cone beam CT per se. There is a group that's dedicated to looking at breast imaging, and they might include breast CT. And there's another group that was looking at dental, and they might look at dental CT, but there's no homogeneous standard there. And I see Jeff has his hand up, so I'll turn it over to him.
And one more, John, I would add to that list for 3D C-arms. So that's task group 238, which is completing its work now. So, yeah, I would say that with that list that you just described, the AAPM has sort of done this work in different places over the last 10 years. And what's lacking now is sort of pulling it all together in a way that is consistent across applications. John, I don't know if you agree with that, but.
Yeah, absolutely. There's a need for what you described, Elliot. It's just sort of a manpower issue and a volunteer organization, of course.
Yes, I understand. Well, thank you for all three of you for really clear and concise and outstanding presentations. And I know I learned a lot, and I'm absolutely sure everybody who's watching now and the many people who will watch the webinar will find it really useful. Thank you.
Elliot, this is Julie. There are 3 questions that were submitted. I'm going to read the last one. When will the Corgi Phantom be commercially available?
Josh, that might be for you.
Yeah, sorry, I just had to unmute.
Okay.
Yeah, I think that is for me. We're hoping to be able to ship these Phantoms probably by the end of September. You know, the 2 things that are going on is the first real production run of these Phantoms has begun. And the other thing is we're doing final integration of the software onto the SMARI platform. And I think we're looking at a window of something towards the end of September at this point.
Good. So that's just a little over a month away. And
the other thing I'll just throw out there quickly, because you know you're talking about Phantoms, and for a long time, and Jeff mentioned that we manufacture the Cat Phantoms also. You know, there's a lot of people for a long time have been using things like the MTF, but there's also been a lot of people who still wanted to hang on to looking at their visual test objects. One of the beauties of this Phantom is because we've gone to really a automated Phantom, is the price is much lower than other CT Phantoms, and this is actually under $3,000.
Thanks. And is there a cost for running the software? So if I buy the Phantom,
the Phantom will include 2 years of software, and then after that there will be like an annual subscription fee per Phantom, so that you know you can scan as many different systems as you want with that Phantom.
Okay, thanks.
Okay, do you want to continue? There's 2 more questions, or have you respond to them individually?
Yeah, I think we're past the hour, so I think we should probably respond individually. If you could just take those down, Julie, though, and maybe we can get a response, and maybe we could even keep that with the webinar. So I think we should probably close. We'll record those 2 questions and try and get answers out quickly. Julie, maybe if you could send those to all of us, that would be optimal. And then thank you all so much. This was really a fantastic presentation, and I have a feeling it's going to be a great resource moving forward in the future. So Julie, any ending administrative issues?
No, that's it. Just a reminder that this session has been recorded, and in the next few days, we will get it up online, and those who are registered will receive an email letting them know it's available, probably with a link to the recording, so that if you want to re-listen or forward it, you're more than welcome to do that.
Great.
So thank you all for participating.
Thank you.
Great job. Take care.
All right. Bye-bye.